Okay, thank you. This is Steve Cole from NASA's Office of Communications in Washington, D.C. We're here today to discuss global sea level rise and the continuing challenge of predicting how fast and how much sea level will rise in the future. Our panel of experts will be giving you an up-to-date outlook on current conditions, what the latest science is telling us, and what NASA is doing to improve our understanding of this complex issue. Our presenters will be speaking to a number of graphics during their remarks. All of these are available online. Let me give you the URL so you can follow along with that. It's go.nasa.gov. That's go.nasa.gov/Rising Seas Briefing. One word, Rising Seas Briefing. After the presentations by our panelists, we'll open it up to questions from the media on the phone lines and to those listening online. If you'd like to ask a question via social media, use the hashtag AskNASA, and we'll take those questions via Twitter. We have three experts on sea level rise science to talk with you today. First will be Steve Nerem, lead for NASA's Sea Level Change Team at the University of Colorado in Boulder, Rignot, glaciologist at the University of California, Irvine, and NASA's Jet Propulsion Laboratory, and Josh Willis, climate scientist, also at NASA's Jet Propulsion Laboratory in California. We're going to start with opening remarks from Mike Freilich, who is director of the Earth Science Division here at NASA headquarters. Over to you, Mike.
Thanks, Steve. Good afternoon to all of you on the phone, and thanks for joining us. Sea level rise is one of the most visible signatures of our changing climate, and rising seas have profound impacts on our nation, our economy, and all of humanity. More than 150 million people, most of them in Asia, live within 1 meter of present sea level. Many more people are threatened by storm surges and extreme coastal phenomena whose impacts are made even worse when the events are superimposed on higher sea levels. Sea level rise will measurably change the shape of our coastline, especially in low-lying states such as Florida. It may entirely eliminate some Pacific island nations, and sea level rise will greatly impact low-lying major cities like Dhaka, Bangladesh, Singapore, and Tokyo. Indeed, even today, normal spring high tides cause street flooding in sections of Miami, something that didn't happen regularly just a few decades ago. Thanks to precision global spaceborne measurements that have been acquired by us at NASA and our partners since 1992, we now know with some certainty that global mean sea levels have been increasing at a rate of more than 3 millimeters per year. These measurements from satellite-mounted instruments called altimeters are amazing feats of NASA technology and science. With measurement precisions of 1 part in 10 to the 8th, that's 1 part in 100 million. The instruments are so sensitive that if they were mounted on a commercial jetliner flying at 40,000 feet, they could detect the bump caused by a dime lying flat on the ground. Not only can we track global average sea level changes, but we also know that some geographical regions are experiencing much greater rates of change and rises, and some regions, sea level is falling systematically. So what you're going to hear from my colleagues today is that by combining spaceborne direct measurements of sea level with a host of other measurements from satellites and from sensors in the oceans themselves, NASA scientists are not only tracking changes in ocean heights, but are also determining the reasons for these changes. We're developing quantitative understanding of how much global mean sea level rise results from thermal expansion of a warming ocean, and how much results from adding water to the ocean by melting land-bound ice sheets and glaciers. We're understanding why sea level is falling rather than rising in some places. and we're constructing models to predict sea level changes in the coming decades and centuries under a variety of different assumed climate regimes. Today, we're really in a challenging and exciting time. Thanks to spaceborne and other monitoring programs that have been instituted over the past 2 decades, we have sufficient data in hand to describe in some detail how sea level has evolved over the last human generation or so. These multi-decadal data sets also serve as an excellent test bed for theories and models that purport to describe why sea level changes in time and in space. As you'll hear, NASA and our interagency and international partners have many new satellite missions that will be launching in the next few years, some of them to continue time series of precision measurements that we're making now, and others to make new measurements of different quantities that will illuminate key processes and the interactions between processes that control our complex planet and environment. Let there be no doubt, this is relevant science, and it will result in understanding that yields direct societal benefit. The effects and the impacts of changing sea level are being felt now in our country and throughout the world. And if the recent past is prologue, the challenges and opportunities associated with changing sea level will become even more important during the lifetimes of our children and our grandchildren. And now I'd like to turn it over to Steve Nerem.
Thanks, Mike. So one of the reasons we want to do this briefing today was that there's been a lot of new research that's come out in the last few years that has presented a different picture than we had, say, back in 2012, 2013, when the last IPCC assessment came out. So we want to use this briefing today to update everyone on where the science stands now and what NASA is doing to advance that science. So the main points I want to make today are that, first, the data show that sea level is rising faster than it was 50 years ago, and it's very likely to get worse in the future. In fact, it's already impacting some low-lying areas. And the biggest uncertainty for predicting future sea level rise is determining how quickly the polar ice sheets will melt in response to warming. And that's just a very difficult problem. But we do have NASA satellite measurements that are telling us with great accuracy how much sea level is rising and what the causes are. And so an interdisciplinary team of scientists are using these data from NASA to better understand the dynamics of large ice sheets and how they respond to a warming planet and how this will affect future sea level rise where you live. So let's go to Figure 1, which has different curves on it, and let's get a little deeper into the points that Mike discussed. So first, the red curve on here represents the record of global mean sea level from that is started in 1992 with Topex Poseidon and has been continued by JASON-1 and JASON-2. So these satellites use precise radars to bounce signals off the ocean surface in order to determine the height of the ocean or sea level. So when these measurements are averaged globally, you get the curve you see there, the red line, and these show that sea level, when averaged globally, is increasing at a rate of about 3.2 millimeters per year over the last 23 years, with an incredible accuracy, really better than 0.5 millimeters per year. Now, we also have another curve on this Figure 1, which is from the GRACE mission. GRACE was launched in 2002, and it gives us further insight into what is causing the observed sea level change that we've seen in the altimetry. So GRACE consists of 2 satellites orbiting the Earth together. They're about 450 kilometers in altitude, but 200 kilometers apart. And there's a microwave ranging system on board that measures the distance between the satellites to very high precision, about 1 micron, which is smaller than the diameter of a red blood cell. So it's really quite an achievement. And as the satellites orbit the Earth, the distance between the satellites changes as ice and water move around on the Earth. And so we measure those changes and then analyze the data to get changes in mass on the surface of the Earth, and I'll show you those results now. So the green curve on Figure 1 shows the changes in ocean mass averaged over the whole globe. And they show that ocean mass has been increasing at a rate of about 1.9 millimeters per year. So by ocean mass, I mean this is changes due to water being added or taken away from the oceans. In this case, the mass is increasing, so water is being added to the oceans. But you can also see that there's a lot of similarity between these two curves, and especially for the short-term variations. And they also show that changes in water on the land due to hydrologic changes, such as changes in rainfall patterns due to El Nino, also affect this curve. A good example you might see is the dip there in 2011, which has been tied to the La Nina then and to flooding that occurred in Australia and other areas around the world. So this is already a big clue for what is causing the changes in sea level that we see in the altimetry. Now let's move on to Figure 2, which is also from GRACE. But GRACE can look not only at the oceans, but it can also look at the land to tell us where the water's coming from. And in this case, we're showing GRACE estimates of mass change, mass loss in Greenland and Antarctica. The blue curve is Antarctica at the top, lower curve is Greenland. The mass loss there since 2002, when GRACE was launched, is about 0.25 millimeters per year for Antarctica and 0.74 millimeters per year for Greenland. So together with these NASA satellite measurements, satellite altimetry and satellite gravity measurements, we can conclude that roughly one-third of the rise of sea level that we see is due to thermal expansion. That's basically when heat goes into the ocean, the water expands just like the mercury in a thermometer does. And one-third is due to the ice melt in Greenland and Antarctica. And then one-third is due to the melting of mountain glaciers outside of Greenland and Antarctica. So let's go on to Figure 3. So satellite altimetry, I just showed you global average sea level change, but it also tells us how the sea level is changing regionally since 1992. And so on Figure 3, the bottom plot shows changes in sea level in centimeters from 1993 through 2013. And you can see there's kind of a distinctive pattern there in the Pacific. And this has been associated with the Pacific Decadal Oscillation, or PDO. The PDO is a natural cycle that is superimposed, or think of happening on top of, the long-term changes from climate. So the bottom plot shows 10 years of satellite altimetry. The top plot shows the last 2 years. And there's an indication that this pattern is changing. It's actually flipping its sign over the last few years. And Josh Willis will discuss the implications of this later. So regional sea level change is also expected to be affected by the melting of the ice sheets, with less sea level change near the ice sheets and more farther away from the ice sheets. And we refer to that as ice sheet fingerprints. And so that's another impact on the regional sea level change that you might see in your backyard. But also, scientists at NASA and other institutions are also studying vertical land movement and how it can exacerbate sea level change in some locations, such as New Orleans. And one way to do that is to use GPS receivers on land that are very precise and measure the vertical land movement. That's another area of important research for sea level change. So we've already experienced about 0.8 degrees centigrade of warming. And paleoclimate research suggests sea level will rise about 2.3 meters for every degree centigrade of warming. But we're uncertain how quickly the ice sheets will melt. So we need to better understand ice sheet dynamics. And Eric, Rignot, and Josh Willis will address this in a minute. So I've been focusing here on NASA satellite measurements. I'd really like to summarize not only the ones I talked about, but all of the measurements that are helping contribute to understanding sea level change and what's going to happen in the future. So I talked about satellite gravity. We have the GRACE mission that launched in 2002. Also, NASA's planning on launching the GRACE follow-on mission in 2017 that will continue those measurements. For ocean altimetry, we've had TOPEX, JASON 1, JASON 2, and hopefully JASON 3 will launch in 2016 to continue that time series. In addition, NASA is developing the SWAT mission for launch in 2020 that will measure sea level across a wide swath of the oceans, 120 kilometers wide. Plus, we have ice altimetry, ISAT, and soon in 2018, ISAT-2 will continue measurements of the height of the ice sheets and how it tells us what it's contributing to sea level change. And finally, NESAR is a SAR mission that's going to launch in late 2020, and among other things, it tells us the velocity of the outlet glaciers of the ice sheets, and that's another clue to how the ice sheets are evolving with the warming. So just to finish up, I'd like to mention that in 2014, NASA formed a new sea level change team that I'm the lead of that's composed of an interdisciplinary team of scientists with expertise in glaciology, hydrology, oceanography, geophysics, and a variety of other fields. And you need all these fields, as you might expect from what I've been talking about here, to actually understand all of the factors that affect future sea level rise. So the primary objective of this team is to improve our knowledge of ice mass loss and regional sea level change so we can better predict future sea level change and its regional variations. Later this year, the team will introduce a web portal containing research from the team, but another excellent source for sea level information can be found at the URL climate.data.gov. So now, Eric Rignot and Josh Willis are both members of this new team, so I'd like to pass this off to them so they can give their perspective on the briefing today. Eric?
Hi, thank you, Steve. We're going to turn our attention a little bit on ice sheets. Ice sheets are contributing to sea level rise sooner and more significantly than anticipated. As Steve said, about one-third of the observed global sea level rise is due to the melting of ice sheets into the ocean. We know that with future warming, ice sheets will dominate sea level rise because they hold a much larger volume of ice than glaciers and ice cap. Paleoclimate records suggest very clearly that with future warming, we may lock ourselves into multiple meter sea level rise. We're talking about 6 meters, 18 feet, and higher of sea level rise. As Steve mentioned, the timescales of this rise is not well constrained by those records. Sea level may rise half a meter per century or several meters per century. We just don't know. More research is needed to constrain those rates from past events. We've never seen an ice sheet collapse in the past. We do not know what it looks like, and past records of collapse of marine-based ice sheets have been bulldozed by re-advances. How ice sheets melt into the ocean? They melt in three different ways. One is from the surface due to warmer air temperature. This is the case in Greenland and for glaciers and ice cap. They also melt from below when ice enters in contact with ocean waters. And the third way is from the periphery when glaciers break up into icebergs that melt and decay in the ocean. That's the important process in Greenland and Antarctica. Surface melt is well understood, and it's projected to increase with future warming. Several NASA teams work in the field every summer to look at the fate of surface melt on and below the ice sheet and how this influences the ice sheet mass balance. And more on this will be discussed on Friday. Next month, you can turn over to Figure 7 here, NASA Operation Icebridge will fly over Greenland to measure how much melt took place this summer in various parts of Greenland. You can see on the figure the spatial coverage of the flight tracks to be covered next month to get an idea. We will cover various ranges of elevation, snow and ice regimes to characterize the changes over the entire ice sheet. So this data will inform us about the magnitude of the 2015 summer melt, so we can compare it with satellite data. We can evaluate our surface melt models, and this also is done in preparation for the data to be collected by ISAT-2 to be launched in 2018. ISAT-2 will continue these observations pole to pole on a continuous basis. In contrast to surface melt, the mechanisms of fast ice melt into the ocean when ice is in contact with the ocean and the breaking up of calving cliffs into icebergs are not well understood. They're not well represented in models and therefore affected by large uncertainties. This is why current model projections, such as IPCC projections, which represent the state-of-the-art in modeling, produce relatively conservative scenarios of ice sheet decay because those models do not yet include the mechanism of fast melt in the ocean and fast ice fracture into the ocean that would prevail during area of rapid or catastrophic ice sheet retreat. So to reduce these uncertainties, NASA is supporting research on multiple fronts. NASA is deploying airborne instruments to measure glacier depths and the shape of sub-ice shelf cavities in Greenland and Antarctica. This is the Icebridge program, which is scheduled to last until at least 2019. We use satellite to observe changes in mass, surface elevation, and speed of the glaciers, and more satellites will be launched, as Steve mentioned, to continue these observations into the next decades. To improve our understanding of ice-ocean interaction, several programs have been launched, including the Ocean Melting Greenland mission that Josh Willis will talk about in a minute. And eventually, this knowledge will be transferred into more reliable ice-ocean atmosphere couple models, which are developed by a growing community of climate modelers. Numerical models need to be run at a much higher vertical and horizontal resolution than today. They need to use better boundary conditions than available today in order to simulate the full complexity of ice sheet systems. We are not there yet, but NASA and other agencies are contributing to making this happen sooner rather than later. Observations combined with observations from partner agencies clearly indicate that significant changes are taking place today on ice sheets. A number of these changes have an irreversible character, meaning it would take centuries to reverse the trend of ice retreat or recover some ice elements that have been lost. I'm thinking about, in particular, about the progressive collapse of ice shelves in the Antarctic Peninsula, which is still ongoing and moving southward. The irreversible retreat of the glaciers in the Amundsen Sea sector of West Antarctica that we talked about in May 2014. This is still ongoing, although we are witnessing a slight pause in the rate of retreat of some of these glaciers. The retreat is proceeding inland. Or the fast retreat of the largest ice stream in Greenland, the Jakobshavn Isbrae. Now I'm asking you to turn on to figures 5 and 6, which were acquired just a few weeks ago. We witnessed a spectacular calving event of Jakobshavn Isbrae in Greenland, which removed 12 square kilometers of ice in one day and pushed the calving front of that glacier farther back than ever before. The glacier keeps retreating rapidly into a deep canyon since 2002, and this summer has seen another series of spectacular calving events from these glaciers. We are likely to see more of those calving events in the coming years as the glacier retreats into deeper ice. This is a marine-based glacier. It will remain in contact with the ocean for decades and centuries as it retreats farther inland, and it contains enough ice to raise global sea level by 0.5 meter. It is just one glacier in Greenland, once all melted to sea. So in summary, there are large uncertainties about the timescale of sea level rise associated with the decay of ice sheets. The rates of sea level rise could range from the lower bound of IPCC projection to its upper range and beyond, if we include extreme scenarios of fast ice breakup and rapid retreat, analog to those experienced in prior warmer periods. Our observations suggest that we should be very cautious to conclude too soon that conservative scenarios are reasonable. They may not be, and this is at the heart of what we, NASA, and other national and international agencies are working on right now. And now I'll pass it on to Josh.
Thank you, Eric. I have had some phone troubles up to now, so if I drop out, my apologies. I'll be back. As Eric mentioned, I am the lead scientist for a new mission to measure oceans and their impact on the Greenland ice sheet. We started this year. The name of the mission is called Oceans Melting Greenland, or OMG for short. And before you ask, yes, I did pick that name while I was deleting old texts off my cell phone. The Oceans Melting Greenland campaign will measure oceans and ice loss around the edges of Greenland for the next 5 years, starting next year and continuing through 2020. We'll be collecting observations, and if you look at Figure 8, you can get an idea of the kinds of observations we'll be collecting. These include radar measurements of the height of the ice near the edges, right where it comes into contact with the water. These glaciers drain the ice sheet into the oceans, and as the oceans warm, the impact of the warming water can be felt right at the ice edge. So in addition, OMG will also collect observations of the ocean directly using expendable probes that are dropped out of an aircraft, and these will continue to be collected through 2020. But we also need to understand the troughs and canyons underneath the water, which allow the warm ocean water to reach up to the glaciers. In Greenland and in most of the waters surrounding it, the ocean actually has warm water underneath cold water. The warm water is salty, so it's heavier, and it sits down at depth. So it has to reach into these canyons carved into the continental shelf by ancient glaciers in order to reach the glaciers and interact with them. So OMG is actually also collecting two different kinds of data to map the shape and depth of the sea floor. Right now, we have just completed the very first phase of a shipborne campaign, which carries a multi-beam echo sounder, which sweeps out measurements of depth along the sea floor. And in Figure 9, you can see some of the very early data from this campaign collected in a fjord called Umanak, which carries a great deal of ice off of the glacier, off of the ice sheet, and into the water. And we now have a much better idea of how the pathways by which this warm water can reach up next to the glaciers and also cause increased melting there. So OMG is looking to measure both the ocean warming and the ice melt over the course of the next 5 years and try and determine just how much the Greenland ice sheet is being melted away at the edges by the ocean. Now, Steve earlier talked about sea level rise, and we also heard from Mike Freilich about how we've been measuring sea level rise over the past 23 years using precision altimeters. In addition to my work on OMG, I'm also the project scientist for the JASON-3 mission, which we hope to launch sometime later this year or early next year as we work out the details of how to get back to space with SpaceX. The animation shown in Figure 10 actually shows the amount of sea level rise that's occurred over the last 22 years as observed by satellite altimeters. And if you look at the animation, you'll see that almost everywhere in the ocean is orange or red, indicating a rise. And this rise has been about 7 centimeters over the last 22 years. However, if you look in more detail, there are regions around the planet where sea level is not actually rising but has fallen or has risen much more quickly than the global average. This is caused for a variety of reasons, and it's one of the main concerns of oceanographers studying sea level change using the satellite altimeter data. The satellite altimeter shows us the complex nature of the sea level problem in places like the North Atlantic, where as the globe spins around, you'll see a large warming and cooling, or high sea level and low sea level, surrounding either side of the Gulf Stream as it veers off of the United States east coast into and carries warm water across the Atlantic. This actually occurs because of a change in either the strength or location of the Gulf Stream, which affects sea level on the long term. Other phenomena, such as the Pacific Decadal Oscillation, which is a large-scale, very long time-scale phenomenon in the Pacific Ocean, which rearranges heat and causes sea levels to rise more quickly in some places than others. This can be seen off the west coast of the United States, where sea levels have actually fallen for the last 22 years on average. Now, the Pacific Decadal Oscillation is thought to be part of a natural cycle occurring in the Pacific Ocean. So in the long run, we expect the sea levels on the west coast to catch up to the global mean and probably even exceed the global mean. So we could be looking at much faster than average sea level rise on the United States east coast sometime in the next 20 or so years. The final animation I'd like to talk about is in Figure 11. And as some of you may already be aware, there is talk of a very large El Nino occurring throughout this winter and having a big impact on rainfall, particularly here in California. This animation shows a comparison of the 1997 El Nino, which was the last really large El Nino to bring changes to the entire weather and climate patterns all the way across the planet. If we compare this year's El Nino to the monster El Nino of 1997, we see that in some ways this El Nino has already exceeded it in size. However, the next few months, and really the next month or two, we will begin to know whether this El Nino will persist through the winter. Certainly there's an El Nino, and it's pretty big, but will it have a big impact on rainfall? The next month or two will really decide that. So with that, I think I'll stop and pass this back over to Steve for questions.
Okay, thanks, Josh. Just a note before we go to questions, we now have Tom Wagner with us. He's our cryosphere program scientist here at NASA headquarters, and he'll take any questions anyone has about NASA's sea level rise program, as Mike Freilich had to leave us for another appointment. Just a reminder, to ask a question via social media, on Twitter, use the hashtag AskNASA, and for the media on the call, to ask a question and put yourself in the queue, just on your phone, type *1. We'll start with a few questions that we've received already via social media. The first is, if seas continues to rise, flooding lowland areas, what will happen to the world's freshwater rivers and streams? Who could take that question? Steve, is that something you could address?
Yeah, it'd be difficult to talk about the direct effects, but certainly, as I mentioned earlier in my slides, sea level is intimately tied to the hydrologic cycle, which is the rivers and streams on the continents. And so as we change the global water cycle, that will definitely have an effect on the water on the continents and thus those rivers and streams eventually.
Hey, this is Tom Wagner from NASA. I just wanted to add a little bit that as sea levels rise, you also get saltwater intrusion into local aquifers, so it pushes back fresh water from coastal areas, and the range of the estuary also changes quite a bit. So there are some impacts to local waterways, particularly in coastal areas, and also freshwater resources that are in the ground.
Okay, thank you. One other question from social media before we go to the journalists on the phone line. What are the biggest specific technological gaps that you have now in studying this problem? Is it the matter of better sensors, modeling, or tools to inform local actions that respond to changes? Eric, would you like to take that one?
Yeah, I can say a few words on that. I think the biggest technological challenge for, in particular, studying the evolutions of ice sheets and how fast they may decay into the ocean is that a lot of these changes are taking place from below the surface, which is much more difficult to observe from satellites than surface processes. We're interested in warm water at depth, which we cannot sense easily from the surface. We're interested in the troughs, the passage for warm water to reach these glaciers, which we cannot easily observe from the surface. And also some of the processes that are taking place at the base of these ice sheets below kilometers of ice, which are challenging. Another challenge that we're facing, I mentioned earlier, is that in order to produce more reliable projection, the models need to reach another level of sophistication, and they need to be run at much higher resolution than a lot of computers are able to do at present. So these are some of the challenges that we're facing.
I would just add to Eric's answer that I think one of the challenges that we face is that we need more time. As the ice sheets are just beginning their collapse and to really decay, we need some time to observe them and watch how this happens. And that's part of the reasoning behind OMG, because we're going to be collecting a series of data over time, and really we hope to see large changes in the ocean and corresponding changes in the ice that will give us a better idea of how these two things might be related. I should also say that I forgot to mention during the primary call that you can learn more about OMG at the following website, omg.jpl.nasa.gov.
And I'll echo Josh's comments on more time, that we do need more time, but we also need to continue the satellite measurements over that time, so we have the clear picture that we need to understand how things are evolving.
Okay, thank you both. Our first question from the phone lines, Carrie Sheridan.
Well, thank you for taking my call. Can you hear me?
Yes, go ahead.
Oh, great. Thanks so much. As journalists, we need to translate this into understandable information for our readers. And I was just wondering if there's anything that you could say should be the takeaway message from what you've learned from the satellite measurements over the past year in terms of, I understand there's a fair amount of uncertainty, but what are we really facing? What are we looking at in this century in particular?
Well, I think this is Josh Willis. I think one of the things that we've learned is that the ice sheets are reacting even faster than we had previously suspected, and that there's a large amount of ice there, and the potential for sea level rise is quite great.
Eric, would you like to add to that?
Yeah, I would just add to this for your readers that I think on a personal level, the data collected over the last few years make me more concerned about rapid of decay of ice sheets than I was in the past. So as we go along, I think we are a little bit more worried about what's happening in the ice sheets.
Okay, thank you. Our next question is from Seth Bornstein, Associated Press. Go ahead, Seth.
Okay, yes, thank you. Continue on that, and I do have a follow-up, maybe for Eric or for any of you. You guys published an awful lot of interesting research last fall, winter, around AGU, I think it was. Timing is the law. And I'm trying to figure out what has changed from then to now. Is there some new research? Is there something new estimations for sea level rise from the West Antarctic ice sheet? I guess basically what I'm coming down to is everything you said to me seems the same things you said last fall, winter. Is there a reason you're doing this now? And is there anything new that I haven't figured out here that I'm missing?
Hey, Seth, this is Tom Wagner from headquarters. Look, the short answer is no. The longer answer is, number one, this is the first time we've put together that 20-year record on the actual sea level rise around the whole planet, and we're showing the complexity of that. The other thing is that in the recent months, you've seen a couple of papers come out trying to do more detailed models of the ice sheets. And the other thing that's happened is now NASA has this sea level change team, which is committed to getting together all the interdisciplinary research to really improve it. And so one of the reasons that I push for this is that, if you look in the IPCC report, you see really, really wide error bars. And what we're trying to do is kind of rip the hood off the research a little bit and let you guys see inside to the detailed work we're doing on this question across the board, from actually radar altimetry of the surface of the ocean and how high it's getting, through to going out and doing our new missions like OMG, which also just started right now and is just going in the field, to go and measure what's going on at the ice ocean front right there.
Okay, and then to follow up, you guys talk an awful lot about ice sheets, and that's what the big thing has been the last couple of years. But with OMG, you are looking at a glacier. Can you expand a little bit on trends with glacier melt and sea level rise, and particularly, and if you don't mind, Alaska glaciers and sea level rise?
Alaska glaciers. Hey, this is Tom again. I'll just take this one. So there's a fascinating paper that actually just came out within the last few weeks that looked at Alaskan glaciers. And the curious thing is that the Alaskan glaciers, we thought the glaciers that end at the ocean looked like they were dumping all their ice into the ocean. The amazing thing is that now that looks like that process has stopped. And our future modeling for Alaskan glaciers is going to be based on the surface mass balance, how much they melt, because that looks to be a bigger factor now. One of the ideas for that hot water from the ocean might be causing ice sheet instability actually came from the work on Alaskan glaciers. But I want to throw this question over to Eric Rignot because I have a feeling he'd like to talk about this too.
No, you made a very good point, Tom. I think when you look across Alaska, Greenland, and Antarctica, you're seeing a whole range of climate variables. We're moving from the very warm areas to the less warm to the very cold. And looking at Alaska glaciers tells us what Greenland would look like probably in a century or a few centuries. And what's happening in Greenland is relevant to what's going to happen to Antarctica in the future as well. So they're all connected pieces of research. It's true that in Alaska, we have now fewer glaciers that reach the ocean because they melted away. In Greenland, the vast majority of the glaciers controlling the mass balance are reaching the ocean, and this is why a program like OMG is so critical to make major advances in understanding these processes. And this carries on also for Antarctica, because a lot of the processes that are taking place in Greenland are also relevant to Antarctic glaciers.
Thank you.
Okay, thank you. Our next question is from Irene Klotz at Reuters. Go ahead, Irene.
Hi, thanks very much. I have a couple of questions. The first, I guess, is kind of a real big picture, which is to anybody who'd like to answer it. What would you like people to do with this information?
I can take it. Hey, this is Tom again from NASA headquarters. The most important thing is this. People need to understand that the planet is not changing, it's also changed. And sea level is rising right now. And the most important thing that I'd like people to do with this is to understand that we have data now for them to use in their planning. And the way that it goes is about risk tolerance. So, for example, if you're going to put in major infrastructure, like a water treatment plant or a power plant in a coastal zone, things where they cost society a lot of money to put in, and you have low tolerance for risk, say from flooding associated with a storm surge or saltwater intrusion or any of those things, we have data that you can now use to estimate what the impacts are going to be in the next 100 years. Now, the error bars are still big, but the point of this teleconference today is to tell you about all the work we're doing to narrow that down. And what I would encourage people to do is to go out and read about this as much as they can. There are resources from the published papers we've talked about, but there are also places like climate.data.gov. Do any of the other speakers want to add into what I've just said?
Yeah, this is Josh. I would just add that I think one of the main takeaways is that people need to be prepared for sea level rise. We're going to continue to have sea level rise for decades and probably centuries. It's not going to stop. The question is, how fast is it going to be? And if you live on a coastline or if you have some economic dependence on a coastline, we have to be prepared for rising seas. It's not a question of when, or it's not a question of how much, but rather when.
Thanks very much. And I have two kind of housekeeping questions for you, Josh. The first is, I might have just misheard you, but when you said that you were talking about the falling levels in the Pacific over the past 22 years, and then you said that, that could change and we could be looking at much faster sea level rise on the U.S. I thought I heard you say East Coast in the next 20 years. Did I mishear you? Did you mean West
sorry,
Coast?
I may have misspoken, but it should be the West Coast. Of course, the East Coast has rising sea levels as well, but they tend to be much steadier. On the West Coast, on the coast of California, Washington, and Oregon, we've certainly seen almost no sea level and a slight sea level drop. But this is a temporary thing. We're going to see sea level rise on our coast. Sometime in the next 20 years, we'll probably see faster than average sea level rise. So we have to be prepared.
Thanks. And then the other question is just about Jason 3. Considering the importance of that mission, are you guys still, do you guys have any problems being next in line when SpaceX resumes flights?
Well, SpaceX and NASA are working together to understand the problem that caused the anomaly on the previous launch. And when everyone's happy, then we'll set a new launch date. And I don't have any real new news on that, except to say that everyone's working really hard and looking forward to launching as soon as we can, as safely as we can.
Okay, thank you. Next question is from Eric Naylor at Discovery News. Go ahead, Eric.
Hi, good afternoon, everybody. Just wanted to get a little context and significance of the recent data from Greenland on this 12 square kilometer hunk of glacier that cracked up. Does this happen every summer? Is this going to, refreeze this winter? I mean, what does this mean? I mean, we can run pictures of it, but I need to know how big a deal it is and some analysis of it.
I can take that. This is Eric. I think this is a continuing and evolving story on Jakobshavn-Isberg, the largest ice stream in Greenland. It's a major feature in Greenland. The retreat started in 2002. It's still ongoing. And some of the calving events that we've seen this summer, which are spectacular because they're very big and they make the ice front retreat farther inland, they were preceded by similar big calving events in 2011, 2010. They are examples of what we are likely to see more and more along the coast of Greenland as the glaciers retreat farther inland. And we are moving into a set of processes where we have very tall calving cliffs that are unstable and start fracturing and break up into icebergs. And the ice front of the glacier starts retreating inland. And as a result, the glacier has more reasons to continue to speed up and retreat. Some of this evolution, we've never seen something like this on that scale before. So what's happening in Jakobshavn-Isberg is extremely important and relevant to other pieces of Greenland. And personally, I am in awe and seeing how fast the ice front, the calving front of this glacier is retreating inland year by year. This big piece of ice that disappeared a few weeks ago is not going to be replaced easily by some re-advance over the winter. We're seeing a continuous retreat of this ice front. It's, of course, modulated by seasonal variations. So you have some oscillations around the mean position, but the ice front is clearly retreating on a steady rate inland into these canyons.
Okay, thank you. Our next question is from Jerry Hume. Go ahead, Jerry.
Hi, yes. I'm with News 13 here in Orlando. So Florida was mentioned at the beginning of the conference call, and I just was wondering what this research means for Florida's coastline in the next century and what should people do now? And I have another question after that.
Okay, Steve, do you want to take that one?
Sure. So Florida is probably one of the more vulnerable areas in the country for sea level rise, as you know. And, right now we're saying that, we've committed to probably more than 3 feet of sea level rise, just based on the warming we've had so far. So I think it's also, difficult to protect some of the areas in Florida because of the limestone that it's built on. So I think this is, in a way, this is kind of a warning call for you guys down there that Florida needs to start thinking about how it's going to deal with this sea level rise that's sure to come.
Okay. And my other question was, how does the combination of sea levels and hurricanes impact our coast and erosion?
Hey, this is Tom. So one of the things that happens is, again, as sea levels rise, the storm surge goes higher up on the coast and causes more damage. I kind of will point out, too, that this is significant enough that NASA Kennedy Space Center actually has an aggressive program to deal with this. It's to the point where they've actually created a map of the center to go and figure out what areas they're going to have to sacrifice and lose and what areas they're going to be able to continue to use so they can launch into the next century. And if you look up on NASA's Earth Observatory site, you can actually see a story about this right now.
All right, thank you.
Thank you. Our next question comes from Tim Folger at National Geographic Online. Go ahead, Tim.
Hi, thank you. Thank you. Is it known why Antarctica's contribution to sea level rise has been less than Greenland's? And one other possibly related question, are we likely to see an acceleration of ice loss with less light being reflected back into space and more light being absorbed by the now ice-free polar seas?
Eric, would you like to address that one?
I'm not sure I caught the first part of the question. Why is Antarctica contributing less than Greenland? Was that the sentence?
Yes.
Yes.
Yeah, in Greenland, we have a response of almost the entire ice sheet to ongoing warming. In Antarctica, we have leakage of ice only from a few sectors. Antarctica is a very big place, and in fact, I would turn it around and say that with only these few sectors of Antarctica contributing right now, it's almost comparable to what's happening to Greenland. And we know that in the future, if more parts of Antarctica react to warming, the signal from Antarctica will obviously overwhelm what's happening in Greenland. The second part of the question, could you?
Yes, the second part of the question was, are we likely to see an acceleration of ice loss in the decades ahead?
We're not likely to see it. We are seeing it right now. In fact, this whole discussion is about sea level rise rising now. We're not talking about futuristic scenarios. Sea level rise is rising 1 foot per century, and we're talking about the possibility of this being 3 feet per century or even 30 feet per century if the ice sheets were to decay in a very rapid mode. The acceleration, we can see it with the Grace record. We can see it with the longer records combining the speed of the glaciers with surface mass balance model. The ice sheets are contributing more every year to sea level rise, and we know that this trend will only continue. There's no reason to expect that the ice sheets will melt in a linear fashion. We know from physics that they will react to warming in a non-linear fashion, meaning the melting of ice sheets will keep increasing faster and faster with time. And that's why some of the measurements collected by NASA and other agencies right now are an important red flag on what's about to come, which is going to be much larger than what we've been witnessing in the past 20, 30 years.
Hey, just to add to that, this is Tom. Your question, I know you were also interested in the loss of sea ice and the change of albedo. That is one of the things that we work on in the Arctic Ocean, is there is warming that gets associated with that. It's kind of a complicated problem, though, too, because when you don't have ice on the surface, you can let more heat out of the ocean. And that's kind of the cutting edge of the research, looking at the relationship between changes in sea ice cover, changes in ocean temperatures, and then also connecting that up to the changes in the land-based ice that's around those.
Okay, thanks. Our next question is from Jonathan Amos at BBC. Go ahead.
Hi, Steve. Thanks very much for that. It's a couple of questions, if I may. The first one, can somebody explain to me the reason behind the difference in the rate of acceleration between the global mean sea level and the global ocean mass? Is that a function of thermal expansion? What's the difference between those two rates?
Yeah, the two rates, this is Steve. The sea level is really the primary causes of the rise, the total rise, is thermal expansion and then the melting of ice, whether it be from glaciers or from the big ice sheets. And so the difference in those curves there is simply due to thermal expansion, mainly.
Right, and my second question is a programmatic one, and I don't know if it was a question more directed at Mike, but I don't know, Josh may be able to have a go at this. In Europe, Jason is being rebadged Sentinel and is being essentially wrapped into the Copernicus program here. What does that mean for the American partnership in that long series of satellites?
Hi, this is Josh. We still certainly want to play a role in the future of satellite altimetry, and I believe there are still discussions underway about exactly what that role will be. But we still have a very strong and vigorous science team which analyzes satellite altimetry data, which is funded by NASA and the French space agency CNES. And we expect to continue to fund a lot of science and also make contributions to this mission, but I think the details are still forthcoming on what exactly the U.S. contribution will be for the Jason CS mission.
Right. Okay. Thanks.
Okay. Our next question is from Amy Green at WMFE. Go ahead, Amy.
Oh, hi there. I am calling from Orlando. I wondered if you could elaborate a little bit more on Florida's picture in the future. You say Florida is one of the most vulnerable places in the country for sea level rise. what are the forces that are combining to create that unique situation for Florida? Certainly there are other populous states like California and Texas with large coastlines. Alaska, of course, is very vulnerable. What is unique about Florida's situation?
This is Steve. It's very simple. Just the elevations of Florida are very low compared to those other places. So as sea level rises, the amount of land that will be inundated is much bigger than in a lot of other places around the country.
I would just add to that very quickly that Florida also is the land on which Florida sits is very porous, and so sea level is salt water is able to intrude underneath and in toward the freshwater supply a little more rapidly in Florida because of the porous land.
Great, thanks.
Okay, thank you. We've got time for one last question here. It's from social media. If all the land ice melted on the planet, how high would sea level rise? Kind of a worst-case scenario for Eric. Is there a number for that, Eric?
I think it's in the range of 60 meters, 180 feet, if all Atlantic ice were to melt.
Okay. Thank you. Well, that's all the questions, so we'll wrap it up. A couple of program notes and links for everybody. This Friday at 1 o'clock Eastern, Goddard Space Flight Center will be hosting a live television program about NASA's research in and on the massive Greenland ice sheet. The event will feature scientists who have been actively conducting field work in Greenland this summer with some extensive video footage of the work they've been performing. To watch that, it'll be streamed online at www.nasa.gov/NASATV. Also, we've set up a website that will be collecting all the materials we're putting out about the rising seas this week, including materials from this press briefing. That URL is www.nasa.gov/risingseas. And you can follow all the activities on social media on 2 new social media accounts from NASA called NASA Sea Level. We have both a Twitter and a Facebook account that just went live this week. And referring back to the web page where graphics are for this press briefing, during the call we added a link to the top of that page if you want to look at that page. For more information, we now have a link titled Sea Level Rise Video Resources. A lot of downloadable high-definition footage and clips there from both data animations and some of the activity that has been going on in Greenland. And just to repeat that URL so everyone has it, it is go.nasa.gov/Rising Seas Briefing. So that comes to the end of our briefing today. Thank you, everybody, for listening. Have a good day. Bye-bye.
Thank you for your participation in today's conference. All participants may disconnect at this time.